Hello all, welcome to the third video of video lecture series of analog and digital communication. In this video, we will give emphasis on amplitude modulation. In the second video, we had studied about the definition of modulation and the need of modulation. There where we got the understanding of what is the requirement of modulation. Here we will go for a particular type of modulation. In the definition, as I have already told you that modulation is a process of conversion of one low frequency signal into a high frequency signal. So frequency translation occurs. When we consider a low frequency, low power message signal, that low frequency, low power message signal do not sufficiently have that capability to transmit to a longer distance. So to facilitate that, to make that possible, we need to take the help of another signal which is called as a carrier signal. That carrier signal is a high frequency, high power signal. So in the process of modulation, what we exactly does, we superimpose the message signal over the carrier signal. When we superimpose the message signal over the carrier signal, that means when we adopt the process of modulation, in that case, some characteristics of the carrier signal changes. These characteristics are maybe amplitude, maybe phase, maybe frequency. That is in case of analog modulation or analog communication. Here we will specifically going to discuss about the case where the amplitude of a carrier signal is changed in accordance with the instantaneous value of a message signal. So here a message signal that impacts upon the carrier, and the carrier signal allows its amplitude to change from an unmodulated value to a modulated one, so that it could able to convert to a new signal which is called as a modulated signal. So in this video we are giving emphasis on certain aspects, so those are there written over here are the outlines of this presentation. So first we will go for the definition of the amplitude modulation. Thereafter we will go for the derivation of the expression of amplitude modulated signal. Thereafter we will know how to draw the frequency spectrum of amplitude modulated signal. Thereafter we will understand how the different components of the amplitude modulated signal are related with each other, that means their power relation. Thereafter at the end we will go for the efficiency of amplitude modulated signal, and at the end we will go for a video where we will summarize the whole discussion in a comprised manner. So first, when it comes to the definition of amplitude modulation signal, what exactly amplitude modulation? Modulation means change. So change in amplitude of whom? Change in amplitude of carrier. So here amplitude of an unmodulated carrier signal occurs in accordance with the instantaneous value of a modulated signal, that means message signal. Whether a message signal is positive, whether a message signal is negative, depending upon that, the amplitude of a carrier signal varies. That's why it is a process of change in amplitude in accordance with the instantaneous value of a message signal, that is written over here. So in modulation, what exactly we take? We take two signals. One is the required signal which is there to be transmitted, and the other signal which is supporting the transmission process. The signal which is required to be transmitted is the information bearing signal, that is the message signal or modulated signal, and the signal which helps in transmission of the information bearing signal is called as the carrier signal. The difference between them is that I have already told that the carrier signal is a high frequency, high power signal, and the message signal or modulating signal is a low frequency, low power signal. So if we compare the frequency level of the carrier and message, that can easily be understood by visualizing the waveform of these two signals. This is the waveform of a message signal or information bearing signal, and this is the waveform of a carrier signal. So as we all know, the definition of frequency is number of cycles per second or number of turns per second. So if we consider this is a unit time, and if we compare the number of cycles, we can easily visualize over here that the carrier is having more number of cycles or more number of turns in comparison to the message. So this implies that the carrier is having high frequency in comparison to the message. Now when this two signals, message signal and carrier signal, they get combined with each other, they are involved in the process of modulation, a new signal results which is called as a modulated signal. Here in case of amplitude modulation, the modulated signal looks like this. So if you look closely, look over here, The modulated, newly generated signal, modulated signal, that is nothing but that is a transferable form of a carrier signal. Here this is the carrier and this one is the modulated signal. So here what happened? The amplitude level, unmodulated amplitude level of the carrier, that is made to vary, that will increase or decrease as per the requirement. Here if you closely look over here, during the positive half of the message signal, the amplitude of the carrier, that is increasing on both the sides, and during the negative half of the message signal, the amplitude of carrier is decreasing in both the sides. So for positive value of message, amplitude is expanding, and for negative value, amplitude is compressing. So in this way we are getting the amplitude modulated signal. Next, so let us move to the derivation of expression of amplitude modulation signal. Now two signals are there. One is message signal, which can be represented by small mt, and a carrier signal which will be represented by small ct. As per our generalized representation of a sinusoidal signal can be represented by its amplitude, and it's represented by a sine function. Here I have represented the two signal, message signal and carrier signal, by taking the cosine function. So here mt becomes am cos omega mt, where am is the amplitude of the message signal and omega m is the frequency of the message signal. And in case of carrier will be represented by ct, small ct, which will be represented by ac cos omega ct. Here ac is the unmodulated amplitude of carrier and omega c is the unmodulated frequency of the carrier. As here we are discussing about the amplitude modulation, here the amplitude of the carrier, unmodulated amplitude AC, that is made to be vary. So a new amplitude will be attained, which is represented by capital A. This is the modulated amplitude and this one is the unmodulated amplitude. Whereas in case of amplitude modulation, the frequency of carrier and the frequency of modulated signal, they remain same. Okay, so that can be easily visualized over here. Frequency means number of turns per second. So here number of cycles per unit time becomes same as the number of cycles per unit time in both the cases, in case of carrier and in case of your modulated signal. Okay. So this new amplitude, modulated amplitude, can be obtained by the combination of the unmodulated amplitude with the message. Here AC is the unmodulated average amplitude of the unmodulated carrier. That can be made varied according to the instantaneous value of message signal. By definition, if you go, that modulation change in amplitude of the carrier occurring due to with respect to the instantaneous value. So this is mt is m cos omega mt. So at every instant when t will change, during that period of time cos omega mt will change, and with the change in cos omega t mt, the whole value will change. And when that mt will add with AC, that means will every time for a particular time instant we are getting a particular new amplitude. So in this way we will get new amplitude. So that can be understood over here. We are placing the whole expression am cos omega mt in place of mt. So AC plus am cos omega mt. Okay, here we have taken AC common from both the terms. So from AC, if we take common AC common, then 1 will be left, and this factor am by AC will be there with cos omega mt. Now that am by AC can be represented by MA, that am subscript A will be called as modulation index or depth of modulation. So by definition, that is the ratio of amplitude of the message signal with to the amplitude of the carrier signal. Next we can take the whole expression of the modulated signal and we have to put the newly derived amplitude expression over here. So in place of A we will place SC whole into 1 plus MA cos omega mt. Now if we elaborate the bracket, open the bracket, then we will have SC which will be multiplied with 1, that becomes SC, which is again multiplied with cos omega ct, that will becomes SC cos omega ct. Similarly AC when it will be multiplied with MA cos omega mt, that will become SC MA cos omega mt, SC MA cos omega mt, and when that will be multiplied with cos omega ct, the whole result will be SC MA cos omega ct into cos omega mt. Now again here this expression can be again means expanded by putting a formula cos A into cos B. Here a cos omega ct will be taken as A and omega mt will be taken as B. So cos A into cos B, which can be replaced by formula, that is 1 by 2 cos A plus B plus cos A minus B. So in that way we will have AC plus MA, AC whole into MA by 2 cos omega C plus omega mt plus cos omega C minus omega mt. So after expanding we will have AC cos omega ct, AC MA by 2 cos omega C plus omega mt plus AC MA by 2 cos omega C minus omega mt. So we will have three expression. One is AC cos omega ct, which represents the carrier. The second one is AC MA by 2 cos omega C plus omega mt, that is the upper sideband, and the AC MA by 2 cos omega C minus omega mt, that represents the lower sideband. Next is the frequency spectrum of AM signal. In the very beginning I have told you the modulation is a process of frequency translation. That means translating the frequency of the message signal virtually from a low level to high level by using a high level carrier signal, high frequency carrier signal. So before modulation, or the frequency of the message becomes omega m. Then when it get combined with, or when it involved in the process of modulation, the resultant frequency will be transformed from the low value omega m to the omega c. Okay. So here referring to the mathematical expression that we are having three sections. One is carrier section, other one is upper sideband, and the third one is lower sideband. So here this one is the carrier portion, and this one the portion between omega c to omega c plus omega m, that becomes the upper sideband. Upper sideband is centrally situated at omega c plus omega m, and lower sideband having the frequency omega c minus omega m. Now that will give us a certain idea about the bandwidth of the modulated signal. We got the idea that modulated signal comprising three parts: carrier, upper sideband, lower sideband. So carrier is having certain frequency, upper sideband is having certain frequency, and lower sideband is having certain frequency. So if we go for the range of frequency, then the range of frequency of modulated signal, that will extend from the frequency of the lower sideband to the frequency of the upper sideband. That means omega c minus omega m to omega c plus omega m. So from those two values we can able to calculate the range of frequency, and that can be calculated by subtracting the value of omega c minus omega m plus omega from omega c plus omega m. So when we subtract omega c minus omega m from omega c plus omega m, the resultant become 2 omega m, which is nothing but the bandwidth of the amplitude modulated signal. Next, let us move to the power relation in AM signal. AM signal comprising of three components. One is carrier, other one is lower sideband, and the third one is the upper sideband. So the power associated with the amplitude modulated signal, that is ultimately the combination of power associated with the carrier portion, and the power associated with the upper sideband, and the power associated with the lower sideband. So if we represent the power associated with amplitude modulated signal as a whole, that will be represented by total power PT. That will become the combination of PC plus PUSB plus PLSB. PC becomes power associated with the carrier. PUSB is the power associated with the upper sideband. PLSB is the power associated with the lower sideband. Now, this power can be derived by taking the voltage level of the signal into consideration. So as you look over here, the power associated with any signal can be related to the voltage associated with that signal by this formula: P is equal to V square by R. Okay, so V is the voltage level of that particular signal. So if we put that formula over here, so in place of P C we will have Vc square by R. In place of P USB we will have V USB square by R. In place of P LSB we will have V LSB square by R. So here what is R? R is something that represents the resistance of the transmitting antenna or receiving antenna whenever we are considering. As we are considering the modulated signal, so that is always associated with the transmitting antenna. Modulated signal is always being transmitted from transmitting end to receiving end with the help of transmitting antenna. So here this is associated with the transmitting antenna. Again, the voltage level that is related to the amplitude level by this formula V is equal to A by root 2. If we put that value A by root 2 in place of V, then we will have this kind of change in expression. BC square becomes AC square by 2. So BC square by R becomes AC square by 2R. Similarly, V LSB square by R becomes AC square MA square by 8R. V USB square by R becomes AC square MA square by 8R. So here if we combine this AC square MA square by 8R and AC square MA square by 8R, that becomes 2 AC square MA square by 8R. 2 and 8 will be cancelled. Resultant will be AC square MA square by 4R. Mind it, AC square MA square by 4R, that is nothing but the power associated with two bands total, means power associated with upper sideband and power associated with lower sideband. And AC square by 2R becomes the power associated with the carrier portion itself. This will be helpful during the calculation of your efficiency. So if we take AC square by 2R common, then what will left? 1 plus MA square by 2. So in place of AC square we have put PC, that means power associated with carrier. So the total power becomes PC whole into 1 plus MA square by 2. This is the expression of power in terms of modulation index and in terms of your total carrier power. Next is the efficiency of the amplitude modulated signal. By definition, efficiency of amplitude modulated signal is nothing but the power associated, ratio of power associated with the sidebands, total sidebands, and the power associated with the total amplitude modulated signal. Now, power associated with sideband means power associated with upper sideband and lower sideband. Power associated with both the upper sideband and lower sideband means USB LSB becomes AC square MA square by 4R. So AC square MA square by 4R is written in place of power in sideband. Next is power, total power. Total power is your AC square by 2R whole into 1 plus MA square by 2. That is written over here, AC square by 2R whole into 1 plus MA square by 2. So if we solve this thing, then we'll have the expression of efficiency as MA square whole divided by 2 plus MA square. So if you want to calculate the, take the finalize or find the value in percentage, value of efficiency in percentage, we have to multiply. Now let us to consider a case where the modulation becomes 100%. In case of modulation becomes 100%, that means modulation index becomes 1. That means amplitude of message signal becomes equal to the amplitude of the carrier signal. In that case, MA becomes 1. So if we put the value of 1 in place of MA, then efficiency becomes 1 whole divided by 2 plus 1 into 100. That means 1 by 3 into 100. That is 33.33%. So forget about 100 to find out the value efficiency in percentage. Then efficiency is 1 by 3 by in a round manner value. Okay. So that means one part becomes the power associated with the sidebands, and the one of the three values is the power associated with the sideband, and that sideband that contains the message signal itself. That means rest 67% is the power which is associated with the carrier portion, and in carrier portion we will not have any message signal itself. That can be understood while visualizing the video, that I will say. So here what happened, see, this is the upper sideband, this is the lower sideband, and the middle one is the carrier portion. Okay. Now if you look over here closely, you are having the sinusoidal value, that means message over that is present in the upper sideband. Even the sinusoidal message is present in the lower sideband. In the carrier portion, you are not having any message. That means in the previous case, that when we got that 33.33%, 33.33% power is associated with upper sideband and lower sideband, and 67% is associated with carrier, where no information is there. That a large amount of power is getting lost That's why we need to think about the modulation index and at what level we have to fix the modulation index. So modulation index can be kept from 0 to 1. We cannot take modulation index exactly 1. So that will make a more loss in power. Okay. So sometimes we prefer 100 means 100% modulation, but many a time we will not prefer 100% modulation. Modulation is kept modulation index value is kept much less than your value from 1. Okay. So if we consider the value of modulation is at 0.5, then we'll have a modulated signal which will be look like this. So here modulation index is kept lower than 1. If we kept modulation index value greater than 1, then what will happen? The amplitude of the message becomes higher than amplitude of carrier. In that case, what would happen? The upper sideband will flow towards the lower sideband and the lower sideband will move towards the upper sideband. In that case, what would happen? Overlapping of the sidebands will occur and that will result a noise over here. That is called as aliasing. Aliasing creates a noise. Okay, so to avoid that, we will have to keep the value of modulation index well less or below than the unity 1. So this is all from my side, and the whole thing that I have just said to you, that will be understood by visualizing this video. Please pay attention to this video.
Welcome to this presentation, Understanding Amplitude Modulation. In this short presentation, we'll discuss the basics of amplitude modulation and also explain AM modulation depth, which is one of the most common measurements made on amplitude modulated signals. Modulation is the process of varying a transmitted carrier in order to convey information. There are three things we can change about a sine wave: its frequency, its phase, and its amplitude. In amplitude modulation, or AM, we convey information by changing the amplitude of the carrier. AM is used in a variety of applications. Most people are, of course, very familiar with the use of AM in radio broadcasting, but there are many other application areas for AM, such as avionics, EMC testing, etc. How do we create AM signals? Most often, AM signals are created using a mixer, the inputs to which are an unmodulated RF carrier and a low frequency modulating signal. The result is a modulated RF carrier, whose time domain envelope is a copy of the modulating signal. In the frequency domain, the information in an AM signal is contained in so-called sidebands that appear both above and below the carrier frequency. If we use a simple 1000 Hz sine wave signal as our modulation source, this modulating signal appears as two tones in spectrum, 1000 Hz above and 1000 Hz below the carrier. Our total signal width is twice the modulating frequency. Human speech, on the other hand, contains very broad and non-uniform spectral content. So if human speech is our modulation source, then our upper and lower sidebands will also be broad and non-uniform, and the total width of our AM modulated signal will be twice the width of the highest modulating frequency. As we've just seen, an AM signal consists of two parts, the unmodulated carrier and two modulated sidebands. The AM modulation index, usually abbreviated with lowercase m, describes the ratio of the carrier and sideband amplitudes. In other words, m is the sideband amplitude divided by the carrier amplitude. We can measure the AM modulation index using two different types of instruments. We can use an oscilloscope to measure modulation index in the time domain, or we can use a spectrum analyzer to measure modulation index in the frequency domain. We'll discuss both methods in this presentation. Note that you may also hear the expression AM modulation depth, that is, the modulation index expressed as a percentage. An AM modulation index of 0.85 is the same thing as an AM modulation depth of 85%. We'll start our explanation of AM modulation depth by looking at an AM signal in the time domain. The amplitude of the carrier wave, the blue line, is changing over time. The red line indicates what's usually called the envelope of the signal. The envelope has a maximum and minimum value. We'll designate the midpoint between these max and min values A sub c, and we'll call the distance between the midpoint and the peaks A sub m. The modulation index m is simply A sub m divided by A sub c. In the time domain, it's very easy to see why we sometimes refer to this as AM modulation depth. In the case of m equals 0.1 or 10% modulation depth, we can see that the envelope doesn't stray very far from the carrier. As the modulation index, or modulation depth, increases, the distance between the max and min envelope values, or the peaks and troughs, also increases. When we get to m equals 0.9 or 90% modulation depth, we have very deep valleys or troughs compared to the shallow valleys when modulation depth was only 10%. In case you were wondering, it is possible to have a modulation index greater than 1. This is called overmodulation. In an overmodulated signal, the carrier exhibits 180-degree phase reversals where the envelope crosses the 0 point. Overmodulation is undesirable because these phase reversals give rise to sidebands that can cause serious interference, sometimes referred to as splatter, in nearby spectrum. As we saw a few moments ago, an AM modulated signal in the frequency domain consists of an unmodulated carrier and two modulated sidebands, one upper sideband and one lower sideband. The values A sub C and A sub M from our time domain discussion are also shown here. Modulation depth M can be calculated in the frequency domain by measuring the difference in amplitude between the carrier and the sidebands. This difference, N, is normally negative and expressed in dBc. We can then calculate modulation index using a simple formula. As we increase the modulation index M, the amplitude of the sidebands also increases. And N, the difference between the carrier and the sidebands, therefore decreases. It's important to note that carrier amplitude is unaffected by modulation depth. Note also that the frequency spacing or distance between the carrier and the sidebands does not depend on modulation depth. In the time domain, we can calculate the modulation index M using an oscilloscope and the so-called trapezoid method. This is done by placing the scope in XY mode, with X being the low frequency modulating signal and Y being the AM modulated RF signal. This causes a trapezoid to appear on the scope display, and modulation index is calculated using the lengths of the two vertical edges, A and B, as well as a simple formula. Scopes generally don't have an automatic measurement functionality for AM modulation depth, and the edge lengths must be determined using manually placed markers. This can decrease measurement accuracy and reliability. The shape of the trapezoid changes as we change modulation index. As modulation index increases, the left edge of the trapezoid begins to shrink, increasing the ratio between these two edges. Note, however, that the width of the trapezoid is unaffected by modulation depth. So in summary, amplitude modulation is used in a wide variety of applications, such as broadcasting, avionics, and EMC. AM signals are generated by mixing an unmodulated RF carrier with a low-frequency modulating signal. If we look at an AM signal in the frequency domain, we see modulation appearing as spectral sidebands, with the total width of the modulating signal being equal to twice the highest modulating frequency. The most common measurement made on AM signals is AM modulation depth, or modulation index, and this can be done using either a spectrum analyzer or an oscilloscope. This concludes our presentation, Understanding Amplitude Modulation. Thanks for watching.
So, from this presentation, I have given you the initial introductory part, and I hope you have understood the introductory part, and the video must have enlightened the more conceptual thing about the amplitude modulation. I hope it has become helpful to you. Thank you.